Hello everyone, thank you for being here today. I'm excited to present our research work titled Label Augmentation as Interclass Data Augmentation for Conditional Image Synthesis with Imbalanced Data. Our paper introduces a novel approach to a significant challenge in the field of image synthesis dealing with imbalanced dataset. This research was conducted by my colleagues and me, and Katsumata, Minh, and Hideki Nakayama at the University of Tokyo. Our work addresses a critical gap in current technology. In many real-world scenarios, data isn't uniformly distributed across different classes, leading to challenges in training models that can generalize well. This is particularly true in fields like medical imaging, where some conditions are rarer than others. One of the most pressing challenges in the field of image synthesis is handling imbalanced dataset. What does this mean? In many scenarios, the data we have is not evenly distributed among different classes. For example, in a dataset of animal images, we might have thousands of cat images, but only have a handful of lion images. Why is this an issue? When training generative models like GANs, generative adversarial networks, such imbalance can lead to biased model. These models might perform especially well for classes with abundant data, but poorly for underrepresented classes. This is not just an academic concern. The implications are vast, span multiple domains in medical imaging. So, for instance, a model trained on imbalanced datasets might excel at diagnosing common disease, but fail at rare yet potentially more dangerous conditions. Similarly, in autonomous vehicle technologies, failing to recognize less common but crucial road signs could lead to hazardous outcomes. Traditional approaches to this problem have included techniques like oversampling minority classes or undersampling majority classes. However, these methods have their limitation in context. Oversampling repeats meaningless features many times, while undersampling may miss learning valuable features in majority classes. Recognizing these challenges, our research proposes a novel approach. We introduce the concept of level augmentation, specifically in the context of conditional image synthesis using GANs. Our aim is to effectively leverage the available data, irrespective of class distribution, to train more robust and generalizable models. To understand the significance of our contribution, let's first look at the existing landscape of image generation methods. Traditional image generation has primarily relied on generative models like GANs or VAEs, as these models have been pivotal in synthesizing high-quality image across various domains. However, a common hurdle in this method is their performance on imbalanced dataset. Most of these models are designed to work best with balanced dataset, where each class is equally presented. In real-world scenarios, in this rarely is the case. As a result, these models tend to underperform on minority classes. One approach to tackle this issue has been data augmentation. Traditional data augmentation methods include geometric transformation like rotation, flipping, scaling, or adjusting brightness, contrast, and so on. These techniques help in creating a more diverse training dataset, but they are ineffective for class imbalance data. This brief overview of related work highlights a significant gap in the field, the lack of effective methods to handle imbalanced dataset in image synthesis. Recognize this gap, our research introduced novel approaches, level augmentation, which we believe addresses this challenge more effectively. Unlike previous methods, our approach does not just augment data, but augment levels in a way that encourages the model to learn more robust representation for underrepresented classes. Let's start with basics. What's an imbalanced dataset? Imagine dataset as a fruit basket. In a balanced dataset, you have an equal number of apples, oranges, and bananas. But in imbalanced dataset, you might find it overflowing with apples, but with only a few bananas and oranges. This is a common scenario in the real-world data, where some classes are overrepresented while others are scarcely present. Why is this problematic? In the context of machine learning, models trained on such data tend to develop a bias towards the majority classes and perform poorly on minority classes. This leads to a lack of generalizability and fairness in the model predictions. Effectiveness of data augmentation can be evaluated by two aspects, affinity and diversity. Affinity quantifies how much augmentation shifts the training data distribution from that learned by a model. Diversity quantifies the complexity of the augmented data with respect to the model and learning procedure. This means the data augmentation with a high affinity and high diversity lead to significant gain in performance of trained models. However, in conditional image synthesis, existing level preserving data augmentation only provides data augmentation with high affinity but low diversity. With this concept in mind, we'll next delve into how our proposed method, source level GAN, aims to overcome these challenges. We have developed unique approaches that not only augment data but strategically augment labels in a way that equips students to handle imbalanced data more effectively. Having understood the challenges posed by imbalanced dataset, let's now turn to our proposed solution. At the heart of soft level again is the concept of level augmentation. Unlike traditional data augmentation that alters the input images, level augmentation manipulates the labels associated with the data contents. This technique involves creating soft labels that are a mixture of existing label classes, thereby enrich the diversity of the training data without physically altering it. The architecture of soft label GAN is an extension of standard conditional GANs. However, it incorporates a unique label augmentation mechanism into the discriminator. This mechanism encourages the discriminator to learn a more nuanced distinction between classes, particularly benefiting the representation of minority classes. In practice, soft label GAN works by blending labels from different classes and presenting these blended labels to the discriminator. For example, instead of strict cat or dog labels, the model might see labels that parts of cat and parts of dog. This encourages the model to generate images that are not just representative of majority classes, but also capture the essence of less represented ones. This approach offers several advantages. It allows for richer training experience without the need of additional data collection. It helps the models to better generalize across different classes, improving its performance on minority classes without compromising the quality of majority class representation. To evaluate the effectiveness of soft level GAN, we utilize diverse range of datasets. This includes anime face, Oxford flowers, imbalanced cipher 10, and hundreds, tiny ImageNet, Stanford cows, and ImageNet long-tail dataset. The choice of these varied datasets serves the dual purpose. First, it allows to test the robustness of soft level GAN across different domains and types of imbalance. Second, it helps demonstrating the generalizability of our method to a wide range of real-world applications. For comprehensive assessments, we use a multiple evaluation metrics. The fresh inception distance, or FID, measures the distance between distribution of generated images and real images, indicating the quality of generated images. Lower FID scores signify better quality. Another metric, the learned perceptual image path similarity, or LPIPS, assess the diversity of the generated images, with a higher score indicating greater diversity. To benchmark the performance of soft level GAN, we compare it against data or level augmentation-based data-efficient conditional GANs. This comparative analysis helps in highlighting the improvements our method brings, particularly in handling imbalanced dataset. This experimental setup, with its diverse dataset and comprehensive metrics, is designed to rigorously test the efficiency of soft level GAN. It underscores our commitment to providing a solution that is not only theoretically sound, but also practically effective across various real-world scenarios. Let's delve into the results obtained from our experiments with soft level GAN. Across all datasets, soft level GAN consistently outperforms baseline models. Notably, FID scores were significantly lower than soft level GAN for soft level GAN, indicating higher quality image generation. Qualitatively, the image generated by soft level GAN has a remarkable improvement. For example, in the standard cars dataset, soft level GAN successfully generate diverse and realistic images. This is a substantial step toward addressing the challenge imposed by imbalanced dataset. In terms of per-class performance, although the augment GAN shows performance drops on underrepresented classes, our method performs consistently for highly represented and underrepresented classes. These results have significant practical implications, for instance, in domains like medical imaging or autonomous driving, where encountering rare scenarios is critical. Soft level GAN ability to generate high-quality, diverse images of underrepresented classes can be immensely beneficial. To conclude, our study introduced soft level GANs and novel approaches to address the challenges of imbalanced datasets in conditional image synthesis. Through the innovative use of level augmentation, soft level GAN demonstrates significantly improvement in generating high-quality and diverse images, particularly for underrepresented classes. Our experiments across various datasets have shown the soft level GAN not only enhance the quality of diverse generated images, as evidenced by lower FID scores, but also boost the diversity indicated by higher LPIPS score. Looking forward, there are several exciting avenues for future researches. One potential area is applying this method to other forms of imbalanced datasets. As we conclude this presentation, I'd like to extend my sincere gratitude of all of you and your attention and engagement. It has been a privilege to share our research with such an esteemed audience. I'd also like to take this opportunity to acknowledge the invaluable contribution of my co-authors. This research represents collaborative effort, and its success is testament to the dedication and expertise of our entire team. Thank you once again for your time and attention. Please drop by my poster in poster session 2 or reach out to us anytime.